The next step in learning how to use EXAFS Neo to analyze EXAFS data is learning how to work with feff.inp or feff input files. Feff calculates the scattering amplitudes and phases necessary to understand how each path is going to contribute to the EXAFS spectrum. So let's go ahead and start EXAFS Neo. We'll go open up a terminal window, and the first thing we have to do is activate our EXAFS environment. And then we have to change to the EXAFS Neo directory, change to the GUI directory, and run the GUI. So EXAFS GUI or EXAFS _ GUI.py. Now I moved my terminal window out here because we'll actually see output. Alright, so the first question is, where do I get feff input files? And the answer to that is, you probably are going to have to make up your own. You may be lucky, depending on what you're actually doing, but you can use either an atoms.input, atoms.inp, or a CIF file with crystal structure data to actually do these calculations. If you're lucky, something you need exists in the atoms.inp archive. So that's at millennia.cars.aps.anl.gov atomsdb. WebAtoms is at millennia.cars.aps.anl.gov/webatoms. And sometimes you have to look under the wrong element, or what I would think is the wrong element. So for example, under oxygen you can find structures for zinc oxide, zinc sulfate, etc. Rather than under zirconium, and you might have to change what's actually the absorbing atom in that case. So I'm going to click on plutonium. Plutonium is my favorite element. So we have FCC plutonium, and I could actually run WebAtoms from here, but I'm just going to hit get atoms.inp file so you can see what it is. I would select this, and then I would paste it into my favorite text editor, which in this case is BBEdit. And then I could go ahead and save this as atoms.inp, and replace the old one. Alright, so then I can come back to WebAtoms, and I can choose my file, and I'm going to open up that atoms.inp file I just saved. Then I have to hit submit crystal data. So hitting submit crystal data actually brings it into the file, and then I usually have to change a few things. So I want to make sure it's feff8 element style, so I can click on that. This will all be fine. I want to increase the size of my cluster for most cases that I'm going to work with EXAFS Neo. So I'm going to change, not 100. I'm going to change that to 10, and I'm going to make the longest path also 10. After I do that, I have to hit compute, and that will change my file. And we can see my paths now go out to a distance of 9.899, which is as close to 10 as I need. And then I can save my feff.inp file. Now, unfortunately, feff actually requires the file to be named feff.inp, so what you find is that you end up having hundreds of feff.inp files on your computer. It gets saved to my downloads folder, so I can open that up. I can't open it up easily, but I can drag it back to my text editor. One thing that you do have to change typically is because EXAFS Neo defaults to using the free version of feff, you have to comment out the SCF card, which does the self-consistent field calculation, which isn't available in the free version, and then you can go ahead and save that. close that because I don't need that. Like I said, it's very likely that you won't find what you want in the atoms.inp database, and so you'll have to work with a CIF file or hand enter the atom positions into your FEFF input file. It's not always the most fun thing to do, but you have to work with FEFF. So let me go back, hide Safari. So I have EXAFS GUI running now. And in EXAFS GUI, I can select a different number of FEFF input folders. It defaults to 1 to 5. And I'm just going to make it 1 right now. But if I want to have multiple FEFF paths from different structures, I can do that by increasing the number of FEFF folders. In fact, let me just make it 2. Let me start by doing a calculation here. I can select choose, and I have TCCL6 ready to go. I select the folder, and it runs the FEFF calculation. I can go into the next one and pick TCOCL4, and it will start that FEFF calculation as well. Now let's say I decide I really know my material is TCCL6. I can go back here and make this 1. Have to choose my directory again, TCCL6. But this time it realizes that the calculation has already been done and doesn't repeat it. So for a data file, I can collect TCCL6, can choose an output file, and we'll make this output, and sure, I'll replace it. Populations, these are values that you typically don't want to change. The number of generations is something that you'll change. The path list now has to include the paths that we just calculated. So if we look, we can scroll back up into our window, and we saw that there were 43 paths that were retained in our TCCL6 calculation. But the dominant one is the first path. So the first and second paths are the dominant contributors, so we could put those in. Actually, that was probably TCCL. I don't remember which one of these I did first, but yes. So anyway, you can go and pick out which FEFF path is the right one for you to put in there and keep. This is also in the paths.dat and the list.dat file, so if you forget, you can always go back into there. So I can always open up TCCL6. Find list.dat, open it up in my text editor. And so for TCCL6, the highest contributing path is the first path, with an amplitude ratio of 100%. These are normalized. If I were to open up TCOCL4, find its list.dat, I can open it up as well. And this one are the first 2 paths. The first one's technetium oxygen, second's technetium technetium. So if I were going to start with just first shell fits, I would start with paths 1. If it was TCCL6, I'd start with paths 1 and 2 if I was TCOCL4. So to do that, I just make a list, 1, 2, 3, 4, etc.